This is the third part of my lecture on descriptive statistics, in which I'm going to talk about measures of central tendency. Central tendency is a bit of a mouthful, but a measure of central tendency is just a rather complicated way of saying that it's a value that quantifies the centre of a distribution. For example, these two distributions have got the same shape, but they've got different central values. The blue distribution is further to the right than the yellow one. It has higher values on average, so there's just a shift between the two distributions. So the central tendency describes the typical value of the distribution. There are several measures of central tendency that we might use. The mode is the most frequently occurring value. The median is the middle value, where half the measurements are bigger than the median and half are smaller than the median. The mean is just the average of all the values. Actually, there are several different sorts of mean, arithmetic mean, geometric mean, harmonic mean, for example. So in these lectures, when I talk about mean, I'm just going to be describing the arithmetic mean. That's what we commonly call the average. Here's an example of looking at the mode, the median, the mean for our bone scan frequency data. We've already seen this histogram of the frequency of different numbers of bone scans each day. So if we look at that distribution, what do you think is the mode, the value that most frequently occurs? Well, clearly the tallest block in that is 6. 6 is the modal value, but it occurs on 5 days more than any other. So the mode is very clear. What about the median value? Remember, the median was the value where half the measurements are below it and half above it. What do you think is the median for this data? Not quite so easy to work out, but if you put a line just here, then there are 1, 2, 3, 4, 5 below it and 1, 2, 3, 4, 5 above it. So that purple line divides the data in two, with 5 measurements below and 5 above. So the median is somewhere between 5 and 6. Let's say it's 5.5. What about the mean? What is the average value? Well, it's impossible to say the average value just by looking at the data. We have to do a calculation. But in a moment we'll see that the average value for this data is in fact 5. So this is an illustration of the fact that mode and median and mean are not necessarily the same. In fact, because our data here is rather skewed to one side, the mode and the median and the mean are distinctly different. If we had nice symmetric distribution, then the mode and the median and the mean might well all be the same. So let's see how we calculate the mean. Well, there's a simple recipe. Step 1, add up all the values. Step 2, divide by the number of values, and that's the mean. Really a very simple recipe. So let's apply it to our bone scan data. We've already seen that we do this number of bone scans. 6 bone scans on the first day, 4 on the second day, 6 on the third day, and so on. And the recipe says that we have to add up all the values. If you add 6 plus 4 plus 6 plus 4 plus 3 plus 6 plus 5 plus 4 plus 6 plus 6, that comes to 50. That's the total number of bone scans we did in all 10 days. Step 2 of the recipe says that we have to take the number of values. In this case there were 10. There were 10 different numbers that we've added up there. That's the number of days when we made our measurements. And then we take the sum of all the values divided by the number of values. 50 divided by 10 is 5. That is the mean. In common English, that's the average number of bone scans that we did each day. So you see, it's a very simple recipe, very easy to calculate. There's nothing frightening at all about calculating the mean. All we do is add up all the values, divide by the number of values, and that's the mean. Now I want to introduce you to a summation notation that's widely used in statistics, and we'll see it applied several times during these lectures. So We've seen how to calculate the mean with a simple recipe. Let's see how that's described by our summation notation. Suppose we got 10 measurements, x1, x2, x3 up to x10. The suffix 1, 2, 3 describe the different measurements. X is the value that we measure. If we want to sum all those measurements, clearly we get x1 plus x2 plus x3 and so on all the way up to plus x10. That's rather a long-winded way of writing things, so we have a shorthand notation where we write sigma xi. Here xi, the I means 1, 2, 3, 4, all the possible values. In this case there were 10 values from 1 to 10, so xi means x1 and then x2 and then x3 all the way up to x10. And the Greek letter sigma is just a summation symbol, which means add up all the numbers. So we read that as sigma xi and we interpret it as add up all the values of x. So using that notation we should be able to translate our recipe into a formula. Here's the formula for the arithmetic mean. If we've got n measurements, x1, x2, x3, x4 all the way up to xn, then the mean is the sum of all those measurements, x1 plus x2 plus x3 all the way up to plus xn, divided by the number of measurements, n. And we'll call that m for the mean. Now in our summation notation that can be written as sigma xi, which means x1 plus x2 and so on, divided by n. So we have a nice simple formula. M is sigma xi divided by n. In my lectures I'm going to use m for the mean, but often in textbooks you will find x bar used instead of m. X bar is just another way of writing the average value of x, which is all the mean is. So m in my lectures is exactly equivalent to x bar in other texts. Let's see how we can apply our formula to our bone scan data. We've already calculated the mean using the recipe. Let's just apply the formula. The formula says we have to calculate sigma xi divided by n. Here's the number of scans each day, and our measurements xi are the 6, 4, 6, 4, 3 and so on. Sigma xi means we add those all up, and that's 50. The sum of all our measurements, sigma xi, is 50. The number of measurements is just 10, so the formula says sigma xi divided by 10 is 50 divided by 10 is 5. That is the formula applied to calculating the mean. And of course it gives exactly the same result as the recipe. The formula is just a mathematical way of writing down the recipe. Use whichever you feel most comfortable with. They will give exactly the same result. So sometimes we have to calculate the mean when we've just got the frequency histogram data instead of the individual measurements. Here we saw that the value 3 bone scans in a day occurred just once, 4 bone scans in a day occurred 3 times, 5 bone scans in a day occurred once, and 6 bone scans in a day occurred 5 times. So the sum of all those measurements is 3 plus 4 plus 4 plus 4 plus 5 plus 6 plus 6 plus 6 plus 6 plus 6. Obviously we can simplify that to 1 3, 3 4s, a 5 and 5 6s. Now if we define Fi to be the frequency of which we get the value xi, then we can rewrite that as f1 x1 plus f2 x2 plus f3 x3 and so on. That means that the value 3 representing x1 just occurred once, so f1 is 1 and x1 is 3. The value 4 occurred 3 times, so when x2 is 4, f2 is 3, and the value 5 occurred once, and the value 6 occurred 5 times. So that's how we can calculate the sum of all the measurements. We also want to know the total number of measurements. Well, clearly there was one block of 1, a block of 3, another block of 1 and a block of 5. But we can just write that as the sum of the frequencies, f1 plus f2 plus f3, adding up the heights of all of those blocks. So if we remember that the formula for the mean was the sum of the measurements divided by the total number of measurements, that means the mean must be f1 x1 plus f2 x2 plus f3 x3 and so on, divided by f1 plus f2 plus f3 and so on. But in our summation notation we can just write that as m is sigma fi xi divided by sigma fi, meaning we add up the product of the frequency and the value and divide by the sum of the frequencies. This is the formula we need to use if we've got the data in our histogram format. So let's have a look at an example using our bone scan frequency histogram. We know that we've got this histogram where the value 3 occurs with a frequency 1, the value 4 occurs with a frequency 3, the value 5 occurs with a frequency of 1, and the value 6 occurs with a frequency of 5. The formula says we have to calculate sigma fi times xi. So let's work out that product. 3 times 1 is 3, 4 times 3 is 12, 5 times 1 is 5, 6 times 5 is 30. Now if we add those up, the sum of the frequencies, 1 plus 3 plus 1 plus 5, adds up to 10, and the sum of the products, 3 plus 12 plus 5 plus 30, adds up to 50. So the formula says we have to divide the sigma fi xi, which is 50, by the sigma fi, which is 10. 50 divided by 10 is 5.0, giving us exactly the same answer as we had when we use the individual measurements, as you would expect. So if you have data as a histogram, this formula is an alternative one you can use to work out the mean. Note that sigma fi, the sum of the frequencies, is always equal to n, the number of measurements. It's just an alternative way of adding up all the measurements. So that's the end of my third part of my talk on descriptive statistics. In the next part we'll look at measures of dispersion.